Robots have an effect on our daily lives. Whether it is from the packaging of our foods or to the manufacturing of our medicines, there is no doubt that the robotics premise is widely used in several aspects of the industrial field. Robots are there to replace humans in repetitive work such as in assembly lines and packaging. One of the most common types of robots in the industrial field is a robotic arm. The robotic arm is used as it has a high resemblance to the actual human arm, which makes it a very useful design for a robot. Even though robots are mostly autonomous, there is still the aim of establishing a human-robot cooperative system. One of the methods to achieve this is via the use of virtual reality. Virtual reality has the capability of being used in the industrial field as it is the new type of immersion that enables us to insert the user in a new world. In other words, it is the bridge between the real world and the virtual world.
While the aim towards the use of robots is to increase work rate, amplify efficiency, and reduce the risk on workers, human-robot collaboration is yet to reach a point to nullify work-related accidents. Locations such as nuclear power plants, ceramic factories, and vehicle painting booths impose a significant safety and health issue for any operator in their work area. Situations like these guide our proposed solution towards a certain criterion, a criterion in which operations performed over a distance is necessary. Our solution to the problem revolves around the use of teleoperation alongside virtual reality to place the operators in a safe simulated work environment. Additionally, AI will be used as to implement the self-aware technique on controlled robots. The integration of tele-operated control through virtual reality with AI may lead to an increase in human-robot collaboration significantly.
Our project, we are using artificial intelligence to control our robotic arm and make it smarter, as an AI solution will lead to an increased control, resilience, quality, and time reduction.
Our aim here is to enable the robotic arm we are working on to create a self-image to itself, so that it can do three important and crucial tasks: adapting to different situations, handling new tasks, and finally detecting and adapting to physical damage or mechanical issues. Self-aware technique is something that we are striving for with our 7 degrees of freedom manipulator, to be able to adapt to any damage or change in the surrounding environment with zero prior knowledge of physics, geometry, or motor dynamics. Therefore, we focused on developing and creating much simpler AI systems like simple neural network.
Our solution is applied on a customized 7 degrees of freedom serial robotic arm. The robotic arm is made of assembled aluminum sheets to make it light in weight and much easier to assemble. The pulleys are made of aluminum as well, while the shafts are made of steel to withstand the high torque. The robotic arm has 7 joints actuated by means of 7 bipolar and closed-loop stepper motors, and each has a gearbox to increase the output torque. 6 of the joints are revolute, mounted on a prismatic joint to increase the workspace of the robot arm and make the robot arm much the same as robots in industrial workplaces. The end effector of the robot arm is a gripper actuated by means of a servo motor for pick-and-place tasks. Our solution allows the robot arm to be operated in different workplaces, performing several tasks such as pick and place from a belt conveyor, welding, and assembling.
The goal of the deep neural network in our problem is to predict the joint's angle that will lead to achieve the desired pose of the end effector without any mathematical calculations. This problem is known as the inverse kinematics problem, and it is one of the main challenges in robotics control. In this stage, we have collected our training data from the simulation, but later the data will be collected from the hardware. In order to do that, we generated the workspace using forward kinematics. The very first step is training the FK and IK neural network using the generated datasets. The architectures of the FK and IK neural networks are shown here. They consist of 10 hidden layers with 1000 neurons for each layer. The only difference is that in the FK neural networks, the inputs are the joint states and the output is the pose, and the opposite is done in the IK neural networks. The training process was done iteratively using Google Colab servers. 16 accounts have been used in parallel to reduce the time. And the second step is connecting the trained neural networks with movie software and verifies output of the neural networks. Afterwards comes the stage of hardware implementation, in which we have used the neural networks model to solve the IK problem for some poses. After calibrating the camera, we have implemented it in the system so that it provides the pose of the objects to the neural network model, and we have tested it as shown in the video.
Unity 3D is a popular free-to-use game and physics engine. It is mainly used to demonstrate 2D and 3D scenarios and give the ability to custom make a virtual world to fit the user. Now shown is a demo of the path planning abilities of our system. The user interacts with a sphere that represents the coordinates of the end effector. The user moves the sphere, making the path desired for the robot to move along. This path consists of several point placements of the sphere, each with its own coordinates. The coordinates are then sent to ROS for kinematics calculations. After the calculations, the joint states of the robot are acquired and sent back to Unity. The user is then able to visualize the predicted motion of the hardware inside the virtual reality. The connection between Unity and ROS is via WebSocket protocol using ROS Short package. This allows the data transfer between the two platforms to operate fast and efficient. Now shown is a demo of the pick and place task for our system. The user picked a box. The coordinates of the box are sent directly to ROS in order to calculate the joints and angles and updates them to Unity. When the end effector reaches the desired pose, it snaps to the box. The coordinate sphere appears. When the box snaps to the end effector, it sends to the gripper motor in the hardware to grasp the box, and then the user is able to use the coordinate sphere to make the desired path in order for the robot to follow. This simulation is planned in Moved Simulation tool in ROS and executed on the real hardware. The user uses the live stream in the virtual scene to check on the motion of the actual hardware. The controllers are used to send commands for returning back to home position. From this demo, we represent the ability of the system where the virtual scene mimics the real one, while achieving higher accuracy and precision. These demos are a showcase for the use of VR in teleoperation and AI to solve for the kinematics.
Our product solves the problem of risk and harm in work environments by merging teleoperation with virtual reality and meshing artificial intelligence to enhance the automotive level of robotics systems. Our vision and future work aim towards implementing a more cooperative solution. Cloud robotics is the integration of the cloud platform's tools and solutions with robotic systems, using Docker to improve our product usability and make it compact, flexible, and easily implemented on any system, and also improving the overall system goal when applied and accessed remotely from any device, anywhere. We envision to apply our system on a multi-user perspective to make it more collaborative and easy accessed. Applying our system in an industrial factory with increasing the number of accessible robots and giving the user the ability to customize the scene to his needs. The simulator demonstrates some of our intended future improvements by customizing your scene according to your need and easily control and program the robotics system in it.
With the world currently facing hardships, people look towards protecting their lives and their loved ones. For that, we thrive towards using human-robot collaboration to make our world a less harmful world, a much safer world.